Good morning. Welcome to this week's session of OneTick Live. Today's topic will be machine learning with OneTick. My name is Tom Finke. I'm a senior engineer with OneMarket Data. And today we'll be talking about OneTick's built-in support for machine learning algorithms, such as classification, regression, and clustering. And we'll walk through some use cases which demonstrate this functionality using OneTick's machine learning event processors. Our sample code is written in Python. As a brief overview of machine learning, of the workflow for machine learning, in general, we need to gather data, determine an appropriate machine learning algorithm, select an implementation platform, pre-process the data, train the machine learning model, use the machine learning model to predict output, and then evaluate the performance of that output. I'd like to show you which machine learning event processors are available with OneTick. OneTick contains 12 event processors relevant to machine learning, some for training. For example, with classification, we support two classification algorithms, the support vector machine and the relevance vector machine. And we also support kernel ridge regression for classification. And for regression, we have two machine learning event processors, one for support vector regression and the other for kernel ridge regression. We have two prediction event processors, one to make predictions based on classification models and the other to make predictions based on regression models. Similarly, we have two performance evaluation event processors, one to evaluate the performance of classification models and the other for regression models. Also, we have two event processors that perform streaming algorithms for machine learning, where the training and the prediction occur in real time. And this can be useful, for example, for real-time applications that utilize OneTick's CEP, complex event processing functionality. And finally, we have one unsupervised learning event processor, and in this case, it's a clustering event processor, and we'll show a demonstration of how that works using k-means clustering. So those are OneTick's available event processors for machine learning. I want to mention that behind the scenes, these event processors use the dlib C++ machine learning library, which is an industry standard machine learning library that supports C++. Also, it's worth mentioning that to set up OneTick to use the machine learning event processors requires only 3 steps. First is to set this configuration parameter of loading the machine learning event processors to true in the OneTick configuration file. Next is to simply add a database called mlroot to your locator configuration file. This database stores the machine learning models. And finally, in your access control file, make sure that this new database, mlroot, has appropriate permissions for the appropriate users and groups. So for today's session, we have 6 use cases that walk through and exercise each of OneTick's machine learning event processors. I think in the time we have available today, we'll probably make it through the first 3, and if time allows, we'll continue with the last 3, and perhaps we'll have another session if we can't make it through all of these. So the first use case is a simple binary classification, just to show how the machine learning event processors work with OneTick. The second use case is a more realistic example of detecting and classifying anomalous orders in an order book. And the third use case is taking those same orders and trying to cluster them into different groups. We'll see if we make it to the regression and deep learning use cases at the end. So moving right along, let's look at use case number 1 for simple binary classification. I'm using a Jupyter notebook here to demonstrate all of these use cases, and the notebook is live, so the first thing I need to do is set up all of my Python modules. So let me run all of those. Okay, so now we are all set up. So let's take a look at what's going on here. First, we have a set of training data that is stored in a OneTick database. The database is called ML_demo_train, and we have a Python function called getData, which is a wrapper around a OneTick query to go and retrieve the data from this database or any database. And if we look at the output here, we have, let's see, 863 examples in our training data set. And this is a binary classification, so we have 2 input features called x1 and x2, and our output predicted training value is in column Y. So let's take a look. Let's visualize this set of training data so that you can see that it's relevant for a machine learning algorithm. We are trying to classify these points as either pluses or dots. So the positive classification training set are the pluses, and the negative classification training set are the dots. So what we want to do is, for any new point on this graph, classify it as either a plus or a dot. And the machine learning algorithms are relevant here because, as you can see, it's not a straightforward linear classification. So I'm not going to walk through too much Python code in this demonstration, but I did want to show you this. This is our code to perform the actual classification, and we're using OneTick's support vector machine classification event processor. And what I'd specifically like to point out is here is the call to OneTick's support vector machine event processor, and we pass in a number of parameters. And 2 of the most important ones are C, which is the regularization parameter for the support vector machine, and gamma, which is a parameter that governs the radial basis kernel used by the support vector machine. So we build up these event processors and send them in here as a list of event processors, and then we send them in to our underlying run query function, and we get a result. And usually what we like to do is convert that result to a pandas data frame, and that's what's going on here. So if we actually run this on our training data set, we can train the model. We can actually train multiple models using different values of those parameters C and gamma. And that's what we've done here. So we've trained 4 different models, 1, 2, 3, 4. And here are the outputs from the training. And another feature that we support is to separate the data into the underlying training data set and also a cross-validation set. So we can specify a percentage of the underlying data that we want to use for cross-validation. And that's what's going on here. So of that, the original 863 data points, we're performing cross-validation on 173 of them. And with that, we can see the performance of the model with the true negatives, true positives, etc. And it's interesting to see that it looks like the best model of these 4 is this one, where C is set to 1 and gamma is set to 50, because it looks like it has the highest accuracy result and also the highest F1 score. And these are ways of predicting performance for a classification model. So for our demonstration here, instead of using a cross-validation set, we're just going to use the entire training data set to train our 4 models. And that's what's going on here. So we're calling the train classification SVM function again 4 times, this time using the entire data set. And so it's telling us we've got 863 examples trained for each of the models. So let's quickly visualize our test data. This is the data that's going to be classified, and as you can imagine, it's simply a grid, 100 by 100 grid of data points. So each one of these data points will be classified into either the plus or the dot class. And the other bit of Python code that I'd like to show is the call to OneTick's prediction event processor. And here it is right here. So it's the mldlib binary classify predict event processor. And of course, we need to pass in the model name so it knows which model it's using to make its predictions. And then, as usual, we set up a list of event processors, pass them into the underlying run query function, and we get our result. And we convert that result into a pandas data frame. So let's see how we did. So for example, with our 4 models that we just trained, we have for example, this set of output for the first model. So this shows that we have made predictions across all 10,000 points in the test data set. So let's take a look at how the prediction worked for the first model. So given those 10,000 points, this is the output from the prediction. So it predicted the blue as the positive classification and the green as the negative classification. And another way to look at this is to show just the boundary curve between the positive and negative classifications. So that's what this plot is showing. And so it would be useful to compare the predicted output of the various trained models to see which one looks the best. which one performs the best. And that is what we're showing right here. So let's take a look at this plot. So here are the 4 models that we used for training and prediction, and set against the original training data set. So you can see that some models are better than others. For example, the red boundary curve line doesn't look like it's doing the best job of predicting the outputs compared with, say, the other boundary curves using different values, different trained values of C and gamma. So this shows that we can easily train models using different input parameters and compare their outputs and make a call about which model fits the data the best. One other thing I'd like to show with this use case is the same thing, only adding in a benchmark against an industry standard machine learning library, and in this case, Python scikit-learn. So what we've done is we've written all the same queries using only Python scikit-learn and compared them with OneTick's output just to make us comfortable that OneTick's output looks reasonable compared with a known benchmark. So here's the same plot with an additional line added. The black line is the output from Python scikit-learn with parameters of c equals 1 and gamma equals 50, which is the same as our orange line from our model using only OneTick. And as you can see, they're pretty close, which is good. That means OneTick is doing its job properly. And the reason why they don't match exactly is because OneTick and scikit-learn use different underlying machine learning libraries. OneTick uses the dlib C++ machine learning library, whereas Python scikit-learn uses svmlib, and they both implement the support vector machine algorithm slightly differently, and that's why we see slightly different results here on this plot of the boundary curves. Let's move on to use case number 2. Use case number 2 is more realistic. What we're trying to do here is detect anomalous orders in an order book. And instead of just 2 input features like we had in use case 1, now we're going to use 8 input features and a lot more training data and a lot more test data. So generally what's going on here is, for an order, we've come up with 8 different features that describe an order, and here they are. So whether it's a buy or a sell, the number of amendments to the order, how long it took to amend the orders, the size of the order, the average size of an order for a particular market maker, and the average return, the ratio of the order to cancel ratio, and then the volatility of the underlying securities in the order. So what we've done is taken these 8 input features and used them to determine if a particular order might be unwanted or as they call toxic, where the trading counterparties may be manipulating the order to generate prices in their favor. So given these features, our experts at OneMarketData came up with a method of determining, based on these features, whether an order may be toxic, may be considered toxic or not. Now this is just our own example for this use case, OneTick customers, of course, would use their own proprietary methods to decide how to pick out suspicious or anomalous orders. So this is just the way we did it for this example, and we would expect that OneTick customers would have their own proprietary way of doing it. So this time we have a large data set of input data. I think we've got about 240,000 orders. And yeah, if we run our query to show the entire data set, we have about 240,000 in here. And what we'd like to do is from that overall data set, take out 50,000 of those orders to be used as the training data set. So that's what's happening here. So we have 50,000 orders. And it would be nice to know, just based on our method, how many anomalous orders are in that training data set. And in this case, we have, what do we have here? 714. So there are definitely some anomalous orders in that training data set. So something important to mention here is, with many machine learning algorithms, you can't just use the raw underlying data. You need to normalize it such that it falls within a given range. Because if you don't do that, some of the input features may overwhelm other input features. So by normalizing, you're giving equal weight to all the different input features for the classification algorithm. And that's what we're doing here. And I should mention that we're doing it all in OneTick with OneTick queries. So after we perform the normalization on those 8 input features, you can kind of see here that the values, instead of the raw values, are now in a range between -1 and +1. So these are the values that will pass into the support vector machine training algorithm to train up the model. So next, we do train up the model, just as we did in use case 1. And we can set aside a portion of the training data set to perform cross-validation. And here we go. With that cross-validation data set, we have some outputs with showing the true negatives, true positives, etc., with an accuracy value and an F1 score. So that looks so far so good. Then with the test data, what we've done to make it a little bit more realistic is taken another set of orders from a different day at a different time, and those will serve as our test data set. And once again, we've grabbed 50,000 of those orders to use as our actual test data set. And once again, we need to pre-process all of that data to normalize the input features. And it's also worth noting that when we perform this normalization, we base it on the parameters that we came up with during training. And then last but not least, we make our predictions. So we've trained, in this example, 2 different models with 2 different values of C, the regularization parameter. And so after we run our query to perform the prediction using the support vector machine model, with the 50,000 examples in our test data set, we have some decent looking output for true negatives and true positives with an accuracy level of 97 or so %. And it's worth noting that using the other model where C is set to 10, we get a slightly better score. We get a slightly better score of, for example, of accuracy. So that means, as an end user, you can experiment with creating models with different parameter values and seeing which one gives the best prediction performance. So that was use case number 2, to use classification to predict an anomalous order in an order book. Use case number 3 uses the same data but a different algorithm. This time we're using an unsupervised learning algorithm called k-means clustering to try to separate the orders into toxic ones versus regular ones. And it's interesting to do this because we can compare how the two algorithms, the results of the two algorithms, and see which one looks more reasonable. So with k-means clustering, here's a snapshot of the actual OneTick query that performs the k-means clustering. And really as usual, we have to normalize our input features. And here's the actual clustering event processor. It's just one event processor. So if we run this query, we run the k-means clustering query, it's going to produce an additional column called the cluster number, and it's either going to be 0 or 1 because we're clustering into only 2 clusters. And the grand finale here, after we've clustered all of our examples in our test data set, we end up with perhaps not actually usable because there are quite a few false negatives and false positives, over 3,000 of each. So in reality, quite a bit of additional analysis would be required to determine how to set up the parameters for the training models and k-means clustering to come up with some output that would actually be usable. But for demonstration purposes, you can see how you might go about doing this using OneTick. So for this OneTick live session, we're about out of time. I think what I'd like to do is have another session where we can show the other 3 use cases because they're also quite interesting. Use case 4 talks about using regression to produce continuously valued predictions as opposed to discrete valued ones from the classification algorithms. Use case 5, which is down here a little bit, does the exact same thing, but in a streaming fashion where the training and prediction are done on the fly as each tick arrives into a OneTick database. And then last but not least, we have an example of using deep learning with neural networks. It's a very simple example with a 3-layer neural network used to classify trade direction. OneTick currently doesn't have any direct neural network event processors. However, all of the underlying data exists in OneTick and is queried from OneTick. And so is still quite useful in performing this kind of analysis. So that's it for this session of OneTick Live, demonstrating how to perform machine learning with OneTick. Thank you for watching and listening, and we hope to see you again soon at the next session. Thanks.